with no guidance. And then we travel so far away. Fly, 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 we fly through the sky. New frontiers can open our minds. No, we're not so far from the dream. Energy brings us life. Running at the midnight, a white light, super love, oh. Until the twilight, the bright skies, super love, oh. Run up to the moon, we will go beyond our reason tonight.
It's my very great pleasure to open up the next lecture in the Metavisionaries series on space. And I'm here with a very good friend of mine, Jim Adams. And Jim Adams has worked in General Electric and in Goddard Space Flight Center before he came down to NASA headquarters and worked as a deputy director in the Planetary Science Division. And then he was asked by the administrator to be the deputy director of the chief technologist. Jim has an enormous amount of experience in spacecraft, and I am really looking forward to his lecture on spacecraft design. Jim, take it away.
Oh, well, thank you, Jim. I hope everybody can hear me. Um, yeah, this is really a unique experience, being able to speak to an audience in the metaverse, and I think it has a lot of potential for the way we might communicate concepts and ideas in the future. Um, Jim's Jim's modest. The best job I ever had was when I worked with him in planetary science. He was my boss, and I did what he said most of the time. Anyway, he uh, he is a remarkable man, and I was encouraged by him and one other person that was in our division to begin doing these kinds of informative lectures. And so I hope you enjoy this one. As we define what a space mission is, at some point we actually have to put together a satellite. And so that's what this particular lecture is about. And I figure we'll just go ahead and get started. Most important thing in designing a space mission is to know what it is you want to do. Oftentimes, especially at NASA, those things are defined by a group of scientists. And the scientists can say, "Oh, we need to go to Europa and measure the radiation levels, or we need to look down on the Earth and measure the rain every 3 hours, or we may have to take solar irradiance measurements. That's how intense is the sun and how is that varying over time." Without that kind of definition, that very high level question, you really don't know what you're going to do. And so it's important to have a team of stakeholders. In my case, it was almost always scientists that have a vision for what it is that they want in terms of data so that they can continue working on their scientific analyses and objectives so that we better understand our place in the solar system and in the universe. So, some fundamental questions to ask yourself is why are we doing this? And what is the mission objective? And how has it been done before? Especially, how has it been done before? Because you want to build on things that have been done before rather than repeat them. And then ultimately, we'll get into this a little bit deeper, but what are the non-negotiable requirements? What must it absolutely do, or the mission is a failure? So, if you think about NASA and all of its space missions, you can think about going to other worlds or exploring the world. and there is always some sort of um, form of the mission. You know, we talk about a rover on Mars, and we immediately know what we're talking about. Or if we talk about an orbiter over the Earth, we automatically know just the general shape of the satellite. Oftentimes, there's missions that fly by, and they take on a different characteristic than the orbiters. So rather than going through all of these are some of the ways that we explore space in terms of the characteristic form of the mission itself. Somebody will say to you, I need a satellite to measure the rainfall on the Earth every 3 hours. That actually starts to form definition of the mission that you're going to design. Then there's an important position, usually in the life of a project, and especially at NASA, we call them mission systems engineers. And the mission systems engineer integrates the science and the design and operations. They're generally the technical conscience of the mission, of the design cycle, I should say, and they tend to provide unbiased advice to the project management as they move forward. And ultimately, they're the keeper of the level 1 requirements and the design process. So, if you look at a typical space mission, there are really 3 elements that get defined. I'll turn around here so I can point. There's the space segment up there at the top, and the ground segment over down here in the lower left, and the user segment. The user segment can be a commercial customer, or it can be a science team, or it can be a specialized group, um, perhaps um, perhaps it's some group that's trying to do a particular kind of observation. But there's always somebody that wants to use the data that you're gathering to do something fly your spacecraft in space. Um, Always, there's more tech available than you can actually fly. And so the question is, what technology, what design form, how much should it cost? How long should we take to build it? All of that sort of thing that goes into a pot to do design trade-off studies so that we can begin to optimize the design and the life cycle of the mission so that we hit the mark for the stakeholders. So an important one is, how long do you want the mission to last? Is it a 90-day mission, or is it a 10-year mission? And then Jim knows all too well, we designed the original Mars rovers, Curiosity or Opportunity and Spirit, to last for 90 days, and they lasted over 10 years. But the the mission lifetime sets a lot of parameters that drive the cost and the amount of redundancy, how much hardware you put on board the spacecraft. And so all of that gets traded off in sort of an iterative process until you're satisfied with the various facets of the space mission design. That could be, you know, you want to get it onto a smaller launch vehicle, or you want to lower the cost, or you need to increase the performance. All of that sort of thing goes into this pot and gets stirred up and comes out as an optimal design. So, for our purposes today, I would say let's choose a mission. And so the objective, I picked one at random: provide data to farmers on cloud movement. That will give you an idea of the kinds of things that stakeholders might ask for. Obviously, cloud movement is important to farming. And so that'll be the objective of this arbitrary space mission that we're going to design today. Some of the constraints would be, you want to be able to make it small enough to launch it as a secondary payload on with some larger mission. That's a way of saving costs. So if you can catch a ride with someone, then you don't have to pay for the whole launch vehicle. They may charge you a fee, but You don't have to pay for the whole thing. And the question is the schedule. How long do you want to take to build it? How long do you want it to last? I kind of chose 3 years, and we maybe a little naively chose the mission to cost less than $100 million. It's a challenge sometimes to build NASA-sized missions for under $100 million. But clearly, if you are in the commercial space, you can build a satellite for $100 million or less. And then our mission will have particular sorts of interfaces. The launch vehicle, how will you get the data down through communications? What's the payload going to be? What's the device that's making the measurement? And who's going to control it? And how will these are all questions that need to get answered over this 3-year design period that we've sort of arbitrarily chosen. Let's see, there we go. So in a classic spacecraft design, there are 10 subsystems: mechanical, propulsion, thermal, attitude and control, attitude determination and control, power conditioning and distribution, electromechanical, wind and control, electronics, communications, flight software, and of course the payload or the science. As we move forward into the commercial space, some of these subsystems may not be present, or they may be combined into multiple they may combine multiple subsystems into a single subsystem, and that's a measure of, as satellites have gotten smaller, you don't need all of these different subsystems. And on a NASA mission, all systems would have a lead engineer, say for mechanical. Then there would be a mechanical engineering team actually doing the design and the analysis, reporting their results to the lead mechanical subsystem engineer, who then also is accountable to the mission systems engineer that we spoke about earlier. So here's a mechanical subsystem. Some of the primary concerns are the structural integrity. The spacecraft has to be supported during the launch period, has to be able to respond to any acoustic noise during the launch period, grounding and electrostatics, thermal performance. It's all here. I use this standard format. What's the primary system concerns for the subsystem? What are the common materials that are used? In the case of mechanical structures, it's aluminum and titanium and beryllium and often carbon fiber. And then over here on the right, what are the design concerns? What are the loads from the launch? That is, how badly does the spacecraft feel the acceleration from the rocket? How does it get vibrated around as a result of the ascent into orbit? And what happens as the spacecraft goes from day to night? It gets hotter and colder, and so thermal expansion of the spacecraft is key, especially if you're flying optical instruments. And then ultimately, how are we going to do a finite element analysis of this spacecraft? So what does finite element analysis? If you have different designs, you need to be able to understand the behavior of those designs under the environment of the launch and of the operational environment, but you really can't go there. So you have to be able to know it in advance. So what we do is we take the design of the spacecraft and we make a grid, and that spacecraft grid then comes out of a CAD model, computer-aided design model, and it goes into a series of software analysis tools that will help us understand the performance of the spacecraft. And in this particular case, the red, this happens to be for thermal. The red would be the regions where it's hottest, and the blue would be the regions where it's coldest. It could also regions of greater stress and regions of lower stress. And those regions where you get red from time to time, there may be areas where you have the design engineer sure a bit so that the spacecraft isn't as stressed during the launch phase. And then ultimately, then the mechanical subsystem engineer is subjected to static load testing. They basically just hang weights on it to see how much weight it can take before it breaks. They put it into a big room and recreate the sound noise from the launch period. They vibrate it, shake it, and then they build an engineering model that then allows the assembly engineers to figure out the correct sequence to put all of the pieces onto the structure. And sometimes there's a pathfinder. That would be a mock-up of the spacecraft that they can then perhaps take down to Kennedy Space Center or the launch site and run it through its paces ahead of time so that we have an idea of the challenges that we'll have when we get down there logistically. And so that's what a finalized mechanical structure would look like. In propulsion, you need to be able to not only move the spacecraft around, but you need to be able to correct the attitude, the angle that the spacecraft is viewing from the Earth or whatever the other object is. And so you design the same way you design a mechanical structure, you design a propulsion system. The primary concerns there are what's the trajectory I'm going to have to correct for? How am I going to insert it into orbit? How am I going to do attitude control? And one of the things we'll get into a little bit later is reaction wheels. They keep the spacecraft stable and pointed in the right direction, but at some point you have to unwind the torque that you've put into them. And so oftentimes we'll use a propulsion system to unload the reaction wheel. It's common fuel types ranging from classic hydrogen all the way down to ion propulsion systems. These slides are available in the study package. Your primary design concerns are what are the mission modes? One that seems to always be a surprise, I don't know why, is the size of the tank and the slosh of the fuel as the spacecraft moves around its target. Sometimes the fuel will slosh, and that can with pointing and that sort of thing. And always concerned about the center of gravity because you're expelling this fuel over the life of the mission, which means then that the center of gravity of the spacecraft is going to be changing. Interestingly enough, the propulsion system is one that you can't test as a subsystem. You have to test the individual pieces and rely on the fact that once you've got it all plumbed together, then it'll seen it perform as a subsystem. There's an example of a rocket motor, an in-space rocket motor. Put hydrazine in this end, and it goes through a cat bed heater here, and it comes out this end as exhaust, and that's what creates the thrust. Propulsion tanks. It's what propulsion tanks look like integrated into a structure. This particular spacecraft actually had 6. Here you can see 3 of them. So when you get into orbit, then your spacecraft is going to be exposed to the sun on one side, Earth down below, and deep space on the other side. And so you've got this heat energy coming in and going out all the time. And the thermal engineer is responsible for trying to figure out how to balance the heat in the spacecraft so that the components in the spacecraft don't get too cold, don't get too hot. We had an example of a partnership between NASA and ESA, where the spacecraft operations team lost control of it, and the propellant in the lines to the rocket engines actually froze up. And so it took a very careful process with the operations team to thaw that spacecraft out. This is a very delicate thing, and it requires an engineer to think carefully about all of the different sources and sinks of heat in the spacecraft and around it. So in this particular case, this is a picture of Messenger, which flew to Mercury, and we built a thermal shield. Looks a little bit like a Roman soldier's shield. So that the rest of the spacecraft actually hid behind the shield in order to stay cool as close to Mercury, much much more warm environment than it would have been around Earth. So we talked about the primary systems concerns, the sources and sinks of heat and how hot or cold we want things to be. There are common components like thermal coatings and radiators and heat pipes and multi-layer insulation. This is an example of a thermal heater. This happens to be a small patch heater, which they come in all sizes. This one is probably the size of postcard. There's that. Don't worry, that spacecraft's not falling over. The reason I chose this picture is these pinwheels on the side are designed to regulate the temperature of the components underneath, and um, as the component underneath gets warmer, and the pinwheel rotates to reveal more and more thermal radiation space. So that in that way, it sort of regulates its own temperature passively. Um, Again, some of the primary design concerns are mission modes and modeling. And here's our finite element analysis again. Same sort of deal as with mechanical. What are the temperatures you want this spacecraft to be able to operate between? Hot and cold when it's operating, hot and cold when it's not operating. Those sorts of things. Then ultimately, once everything's put together, there'll be a system level thermal balance test. And that's a really big deal in the life of the design of a thermal subsystem. We put it in a vacuum chamber, pull the oxygen out of it, and we change the thermal environment for the spacecraft and watch how it responds. An Earth system attitude control system, an Earth observing spacecraft attitude determination and control subsystem has a large number of components. Get put together in a loop, which I hope you can see here. We are looking for we know where it is. We know what state we want it to be in. We know the way it's supposed to respond to the various inputs from the momentum wheels and the magnetic coils. And then, of course, we've got sensors on board, digital sun sensors and gyroscopes and magnetometers that tell us how well we're doing in terms of keeping the spacecraft. Here's some of the components: a momentum wheel, a gyroscope, mag torquer, sun sensor. I think maybe now would be a good time to take a quick little pause. What we thought we'd do is come over here. We've got a garage full of spacecraft parts. And I'll pick a structure that already has propellant tanks in it. This one looks pretty good. There we go. We'll start building a spacecraft right here on stage. Here we go, and you can see there's a structure, and it's got propulsion tanks inside of it. We will need thermal control materials. Actually, let's put up the attitude control pieces first here. I'll do that. Oops. Here's oh, there we go. Thank you, Camilla. Put that subsystem on the spacecraft. And if you can see, there's a thermal control shield here that Camilla has helped me with. And that would go over particularly warm boxes. So I'm going to place that right here. And then we'll need some sensors and thrusters. I saw them somewhere in our garage. Here's a set of thrusters. But sometimes it's hard to grab. Oh, maybe we'll do this one. There we go. Yeah, Camilla's got a set of thrusters. And put those on the spacecraft. Now, I'm not being really careful about where these are going. Ultimately, design engineers would be very methodical about placing these things. But they're here just representative. Camilla, did you put your? Yeah, you did. You put your thrusters on. Okay. So that's the attitude determination control panel with a thermal control system over top of it, propulsion system with thrusters and a structure. Let's see. There's some examples of an attitude determination control systems. These happen to be momentum measurement units, ring laser gyros. That was the phrase I was looking for. And they will help the spacecraft understand how its rate of change, how its pointing angle is changing. It gives it a rate, and then the spacecraft can run through that loop that we talked about earlier. It's a software program to determine whether or not it needs to make some adjustments with the propulsion system. Oftentimes, what happens is, in order to test such a complicated subsystem, is project will create something called flat sat and an engineering model. So they'll take the engineering models of the components and wire them up the way they are on the spacecraft, and they can actually simulate the performance of the spacecraft using the flat sat. See, that's an example of a magnetic torquer. It's basically a magnetic bar. It's an electromagnet that is designed to react against, push against the magnetic field of the Earth. And in that way, you can actually push the spacecraft around using magnetic fields. There's some Earth sensors and a sun sensor. And then we get into power. So let's talk about power for a minute. Most spacecraft get their power from the sun. And so we'll grab it. These ones really want to be grabbed anyway, so let's grab this one. Oh, this one's good. Okay. So put together this solar array on top of a spacecraft. And it collects, it collects power from the sun. And then what do you do with that power? Well, you've got to put it, you've got to condition it, make sure it's the right voltage and that it goes to the right location. So we have a panel here that Cam found for us that's, we'll call this our power distribution panel. So the electricity would be collected by the solar array, come into the spacecraft, be conditioned by the panel, and then redistributed out throughout the spacecraft to the components that need power. That's really important because there are periods of time when the spacecraft doesn't have solar power input. It's behind the Earth, and so it's in shadow, and so there'll be batteries as well. In fact, I think I have a picture of a battery here somewhere. Yeah, there's a picture of a battery. It's not very pretty, but it actually is the life of the spacecraft. So power systems engineers are constantly concerned about the power balance, how much power is going into the battery versus how much power the spacecraft is using, and making sure that for each phase of the mission, there'll be enough power regardless of whether the sun is shining on the solar array. Some of the primary design concerns are pointing the solar rays, power conditioning we've talked about, how much redundancy you need in case one component fails. Do you need a second one? That's usually driven by the desired lifetime of the mission. And how does the spacecraft respond to faults that it detects, and what does it do to control those sorts of things, either through an autonomous operation, or sometimes it'll just drop into a safe position. It'll orient the solar rays towards the sun and make sure that the spacecraft stays safe until the operations team can come back to it and figure out what went wrong. More examples of flat stat testing and mission mode simulation. Command and control key in understanding the operation of the power subsystem. That's a power conditioning box. And of course, once you've conditioned the power, you have to get it somewhere. And so distributing the power, even in this day and age of wireless connectivity, is by wires. And that's one of the things that starts to look um, old-fashioned, if you will, about spacecraft, is you still have to have these wires snaking around the spacecraft. And sometimes it can get kind of unwieldy. You have power wires, you have data wires, you have telemetry wires, and you have to know where all of them are going and hopefully not get your wires crossed. Won't talk too much about electromechanical, except to say that there are times when you need a mechanical operation to respond, and the best way to do that is to move a machine by using electricity. So there's an electromechanical components that will do everything from releasing retained mechanisms to rotating parts of a spacecraft to ensure that they are constantly pointing in the direction that you want. Some of the concerns there, again, are redundancy. How do you deal with debris? In the case of a boom operating, how do you dampen the end of travel so that you don't shake the spacecraft too badly? And how many cycles over the lifetime you would have? Lots of these things get tested for hot and cold modes, and oftentimes will require 200 cycles, even though the mechanical piece may only once or twice in the course of the mission, because we want confidence. There's command and data handling, almost as complicated in terms of number of components as the attitude, determination, and control. It's like the central computer. And think about all of the different peripherals you put on your computers at home. It's the same deal with a spacecraft. You'll have a central computer that will have access to all the other components, usually over some sort of bus. You'll have data storage. You will have the ability to encrypt and decrypt data and signals. Has to figure out what to do if it detects a failure. It's usually the heart of the autonomy system, and some of the other electronics concerns are what's the effect of radiation or thermal on the components? How do you get the right kind of multi-layer circuit cards in order to be able to build these electronics? One of the characteristics of testing and command and data handling is number of hours of failure-free operation. So we would operate this system with and expect that we get something like 200 hours of operations with no failures. And if that's the case, then we begin to have confidence in the hardware that we build. Again, hot and cold cases and control sequence simulations are also important. Flight software, there's really no good way to draw a picture of the flight software, but primary concerns of the flight software are how to execute commands, how to monitor the state and health of the spacecraft, recording telemetry, getting it set up to downlink through the communication system, supporting the attitude determination and control system. A lot of this is tested as lines of code, as modules of code, and then ultimately put together as a system of code. System integration and control sequence simulation are key to all of, or assuring that the flight software subsystem is working well. So now we get into communication. So we got the spacecraft, it's got a structure, it's got a propulsion system, it's got power, it's attitude control and command and data handling. But you've got to be able to tell it what to do from the ground, and you've got to be able to get the data back from space once you've collected it. And so primary system concerns in communications are the uplink and downlink data, the RF spectrum control, spacecraft IDs, how do you decrypt the command, and what's the lifetime going to be? Some of the common components are antennas. You often see those on spacecraft. They're dominant in terms of the footprint of the spacecraft. Amplifiers, transponders, and switching devices. In fact, let's go over to the garage here, and we'll pick an antenna to put on our model. Let's see, let's pick a good one here. Well, this one looks pretty good. Let's see if I can grab that one. All right, there's Camilla, and Camilla's put a small antenna on the on our model spacecraft. Those antennas would be used. Go ahead and leave it where you had it there, Camilla. Thank you. Those antennas would be used because they have a spherical coverage around the spacecraft. So no matter where the spacecraft is pointing, those antennas would be able to communicate with the Earth. The problem with that is that the data rate from those little antennas is very low. But if there's an emergency and you need to get into the spacecraft, you don't need high data rate, you need reliable communication. This dish that I put on board, that represents a high rate communication, but only can irradiate a certain portion of the Earth at any given time. And so it's a very closed beam. And if the spacecraft were tumbling, you'd only be able to see it every once in a while. So you actually need both kinds of antennas on board the spacecraft, one for emergencies and one for normal operations. Let's see. Again, the testing and the number of failure-free hours is key to assure ourselves that it's going to operate reliably, the hot and the cold cases, and integrating it into a system. In this particular case, I'm showing you a picture of one of the tiniest antennas NASA flies. I know it looks like a bent paperclip, but it's actually designed specifically to radiate a particular frequency, a particular data rate in a particular way so that it can meet the mission requirements. And above is an image of a spacecraft transponder where the signals would come in and be turned right back around and go back down to the Earth. And in that way, we can actually measure the distance between the spacecraft and the Earth. Some of these antennas get quite big. This is an artist's concept of TIRS, which is the tracking and data relay satellite system NASA has. These antennas, I believe, are 10 meters across. So all of this, then we've got our spacecraft here on stage. All of this is designed to support the mission. And the mission in our straw man case was to look at clouds. Well, that means that we need a science payload of some sort, and we'll put cameras on board the spacecraft in order to look down at the Earth and take pictures of the clouds, and then it'll go. The data that's collected will go through the command and data handling subsystem, and then out over the communication systems and down to Earth to be linked to the computers of the stakeholders. Same sort of concerns with the science payload as with the rest of the subsystems. What, how's it going to perform? What is it that we need it to do? What about reliability and redundancy? What's the mass and the power going to be? How many failure-free hours of operation do we need? What are the hot and cold cases, and how are you going to control it? The difference is that often the payload itself will come from a different organization than the organization building the spacecraft. Thanks, Cam. Cam's picked a set of cameras. See if I can adjust them just a little bit here. And so we've got these cameras. Cam, it's not letting me pick it up. Maybe if I get in real close. There we go. Okay, so you can see on this. Yeah, you can see if we can turn it around just a little bit. There we go. That inside there are a series of cameras that that are designed to take a variety of different kinds of pictures of the Earth. The shield that's around it is common. It's called a sun shield. It's designed to keep stray light from getting into the sensitive optics of the camera. We'll put it right here on the bottom side of the spacecraft. All right. So now we have a complete spacecraft in concept, of course. Would probably look a little better if the subsystem panels weren't cockeyed and that sort of thing. But in general, that's how a spacecraft goes together. See if I can. Here we go. Once you've got spacecraft together, then you have to take it to a launch site and integrate it with the launch vehicle. A spacecraft that's sitting on top of a launch vehicle adapter, and these big shells on either side of it are the fairing that encapsulate it during the launch, so that the spacecraft isn't damaged by the rushing wind as it ascends through the atmosphere. So you assemble the spacecraft, take it to the launch site, you fill the tanks full of fuel at the launch site because that's the safest place to do that. Put it inside the rocket fairing, then the whole thing gets put on top of a rocket and launched. And in this particular case, there's a sequence where Jason 1 was launched and took off. And as the rocket ascends, all of these different pieces of the rocket get thrown away. They drop into the ocean. And what's left at the very end is your spacecraft that you designed floating on orbit, hopefully. It's when the command and control team takes over. They start talking to the spacecraft through the antennas. They take control of it. They assure that it's stabilized, and the spacecraft is ready for use, for checkout. And ultimately, then we'll be able to take pictures of clouds, send data to farmers. I think that's it. Oftentimes, I've heard from especially high school students when I talk to them about spacecraft design. Well, if I'm interested in this sort of thing, what should I study when I get to university? So in the notes, there's a list of suggestions. Like if you're particularly interested in command and control electronics, what should I study? Well, electrical and computer engineering would be ideal. And on the other hand, if you're interested in thermal, then you might want to study physics and mechanical engineering. So with that, CAM has a number of pre-assembled models that look way better than the ones that we've assembled here today. Maybe Cam, you could bring the big one up and we'll set it up on stage and then turn the satellite kit off so that people then can focus on that. On the, where'd it go? Is it this one up here? Yeah, bring that one on down. That's good. And you can see somebody's put a lot of time, taken a lot of time to put this spacecraft together. And you can see there's cameras, there's communications antennas, there's electronics boxes, structure, and there's propulsion tanks, and even an ion engine backside. So solar arrays, the whole thing, very common for a spacecraft. But every that we would design, because it's designed, each spacecraft is designed to meet a different mission, and because the requirements are optimized, each spacecraft looks a little different. There's another one floating up top there. So that's it for my lecture. I hope you've enjoyed it. I certainly have, and I would encourage any questions now.
So, Jim Adams, I have a question here from Brian. And the question is, how does the design team incorporate biomimicry, if they do at all, and incorporate generative AI in the conceptual phase?
So, what's really interesting is that biomimicry and AI are concepts that are just now becoming thought about on space missions. But some rudimentary biomimicry would be like, if we go to Mars, you need to move around. Well, let's put a rover on the surface of Mars. That kind of simulates crawler, some sort of biological element that would crawl. When we finally go to Europa and delve beneath its ice core, we may use a submarine or a fish. Sometimes there is a constellation of spacecraft referred to as doves, largely because they fly in a constellation in the same sort of way a dove might, or a group of doves might. But in terms of the details of biomimicry, we haven't quite gotten there yet. AI is still a thing that spacecraft engineers are trying to integrate, but they're going very slowly because they want to be able to test it. If you go to the trouble of building $1 billion mission and sending it to Jupiter, you want to be sure that it's going to operate properly, because you can't get to it to fix it. So understanding ins and outs of AI and the idiosyncrasies of artificial intelligence, while it may be helpful in concept, there's also a lot that you don't know about it. And so even today, we're trying to move from what we used to call command and control sequences to autonomy states, and then we are working our way from autonomy states into the idea of some sort of machine learning algorithm, and ultimately maybe we'll end up with AI. Yeah, that's a great question.
Here's another
Dr.
question.
Green has a question.
Sorry, let me just overlook this. What excites you about spacecraft design most, or over the years?
Over the years, I have been involved in over 30 successful space missions. And what I think is what floats my boat the most is the idea that we've got a problem and that we can design a system to help us solve that problem. So there's a potential And if you know me, it is the potential of anything that floats my boat. But in this particular case, why design a spacecraft? Because you can solve a problem for someone. And that's probably a little esoteric, but yeah, that's what floats my boat. And Jim, you were going to make a comment.
I was just going to ask a question concerning another type of power that's used. It's radioisotope power, and we use that instead of solar panels. Why is that the case?
Yeah. So, um, you know, 90 or 95% of the solar system is dark. There isn't any sun where we go, and especially where you and I went, Jim. Right? Sending spacecraft out to Pluto uh, and Cassini at Saturn and Juno at Jupiter. Um, so one of the solutions that um, the Department of Energy and NASA came up with in the late 50s and early 60s is to take a radioisotope known as plutonium-238. It's very dangerous. It's not the kind of plutonium you can make a bomb out of, but it's still hazardous, very, very hazardous. And it generates heat of years or so, and generates heat. Well, you can take that heat and using thermocouples, make a voltage. And if you do that in enough, you do that with enough thermocouples, you can actually make enough voltage and amperage to power a whole spacecraft. So, so just by the heat of the decay of the radioisotope material, you can create power. So the interesting thing about that, though, is that you don't get much power. So you get about as much as a standard light bulb. And what that means then is that the design engineers have to be very careful about how they use their power, how they create the power balance on board the spacecraft. That's a great question too, Jim. There's the other interesting thing about all of this is as we began to get better and better with radioisotope thermal electric power systems, that's what they're called, then the solar array guys felt the competition. And so now today we've been able to fly solar arrays, Jupiter, and oh goodness, Jim, what was the name of that mission that went out to the Trojans? Um, uh, anyway, a number of missions much further out than Mars. Because now we have the technology to push solar array uses of solar arrays much further into space. At some point, though, the sun will just be too dim to illuminate a solar array, and we'll need to continue to use radioisotope power systems.
Got a question here from Tapahide, and it's what about space as a service? Could I just provide
What
a
about
payload
space?
and commercial space file and send?
Say the last part again.
So the question is, can we just provide a payload and a commercial service flies it and sends data back?
Yeah. First off, hi, Tupper. It's been a long time since we've had a chance to talk, but Tupper is an accomplished spacecraft engineer of his own, on his own right. And both Jim and I have worked with him successfully over the years. But he's right. There's this emerging commercial industry that can enable organizations like NASA or other organizations, stakeholder organizations, to simply put a tender out and say, I need data on the clouds and how they're covering farmlands. And then there's a commercial entity out there that will say, hey, well, we've got data that we've already got that we're receiving that we can put together in a product that would meet that need. Or maybe they don't have the data, but they've got a partnership with someone where they can build a spacecraft and then turn around and sell that data not only to the stakeholder, but to other organizations around the world that would also need the data. It's an expansion of commercial enterprise into the space environment. And I'm crazy excited about it because it says that now governments are no longer the sole occupiers of space, but commercial enterprise, the private sector, begin to make headway in that area, and that will enable the governments to do things that commercial enterprise can't or won't.
That was
Another question?
no, that was absolutely fantastic. Jim Green, do you want to come down? We'd love to have a quick fire session with you two. It's not often we get both of you in the same environment.
Yeah, great
say-
lecture, Jim. I really thoroughly enjoyed it. We had a wonderful time, and it sounds like a great audience. This is an interesting little cube.
No, who put that up there? Was it Cam? Did you do this?
Right. So
Yes, that's the model of the ice cubes.
so one of the questions was about
Oh,
commercialization,
cubes.
and we're building space
Yeah.
innovation labs. Jim Green, you want to tell people what that's about and how this cube is actually going to be flying in a couple of weeks, looking at patients with diabetes and foot ulcers?
Yes, be happy to. So this little cube, it's actually a much larger than our, with respect to our avatars, than it really is. It's more like maybe 15 or 20 centimeters on each side. So this is an expansion of that. Now, in this can be any kind of experiment, and this will be plugged into a fabulous unit up in on space station, taking all kinds of data. And our first one, our first major ice cube, is it has cells in it from diabetes patients, and along with the microbiome that interact with that, and we're going to see how that changes in the environment of microgravity on the International Space Station. So once again, a free-flying spacecraft produced some really outstanding results. And now we have an opportunity for many people to get involved in the space systems by building something that's flying on a large spacecraft structure like the International Space Station, which has the same components. It has solar cells, it's got attitude, power, it's got command and control, flight software, and all the thermal aspects, everything. Load. Of course, to command and control it, you're building these space innovation centers at various universities where students can come in and download their data as the International Space Station flies by, and analyze it and send up new commands and really interact in really an important and unique way, more than we ever have in the past. So this is really a new era of opening up the commercial sector, opening up universities and students' ideas to low Earth orbit.
If I could just interject, Jim, really quickly. Yeah, I think the beauty of something like ice cubes going on a facility like the International Space Station is that access to space, the barriers to the access to space are lowered quite a bit. You could be at university and design a payload, and it's not out of the realm of possibility that you can fly it to the International Space Station.
Right. Here it is. Yeah,
Right.
pretty spectacular. Once again, Jim, thanks so much for a tremendous lecture. I really thoroughly enjoyed it. All these elements have to be considered when going into space based on the objective that you have. Some can be minimized, some can be quite elaborate. And indeed, as Jim mentioned, there's a process for which you have to put all this together, actually accomplish the requirements necessary to get your payload in space and your data back to you to analyze. Thanks again.
Thank you, Jim. It was a pleasure putting this together, and I hope to do a few more of them for you.
So Jim, before you disappear and Jim Green, we're just gonna play some music and enjoy all the hard work that's gone in today.
Galaxies unknown.
Why don't you guys come down?
Technology with no guidance. Yeah, we travel so far away. Fly, 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 we fly through the sky.
This is gonna be going in a couple of weeks.
Frontiers can
I did
open
have
our minds. Now we're not so far from
Oh, we could be on the microphone.
energy brings us life. Running at the midnight, a white light, supernova, until the twilight, the bright skies, supernova, up to the moon, we will go beyond the reason tonight.
Awesome.
Oh, I like that.
Oh, there's the sun.
All right.
So-
I am almost out
How
of
long
power.
did that take? What time is it?
Just like 40 or sorry, 57 minutes.
Really?
Yeah, right at an hour.
I hope people
We
weren't
threw the
bored.
music in, and we threw the music in, and it's now 5 o'clock.
Amazing. Well, listen, I'm operating on only a few